Okay, so today we start a discussion of derivatives and their applications. And so we start with this tale of the alien engineer. So why an alien engineer? Well, because we have to make some key changes. So on a planet just like Earth, except for a lack of air resistance, so we take that out of play, a first year engineering student drops a small object from a height of 1.7658 meters and uses a sophisticated timer to determine the ball strikes the ground at 0.6000 seconds. So one thing is here, he has a very accurate measuring devices, which is going to give us a lot of significant figures to keep up with. And the first thing he wants to know is, given these things, what's the average velocity? Well, what is velocity? So velocity is the rate at which something moves. And so velocity, and we've talked about this with other things in previous units, is distance over time. More specifically, it's our change, for this problem, it's our change in height over our change in time. And so the factors that we know here are that the ball dropped from a height of, it was at 1.7658 meters at the start, and it ended at a height of 0 meters. And our initial time was time 0, and we finished at 0.6000 seconds. So we can plug those in and determine exactly what that difference was. So sorry, I had a little bit of trouble with my calculator. 1.7658 divided by 0.6. So we get negative 2.943, and the units would be meters per second. Notice also we get a negative value because it's falling. So we would expect the velocity to be negative. So that's fine. So we have a value for that. Part B asks, what is the velocity of the object the instant it strikes the ground? So how can we determine? We know the velocity at time 0 was 0, and we know the average velocity is negative 2.3 meters per second. But that tells us that it's changing over time. And so at TF, what is that velocity? We can't really tell. We need more information. We've only been able to track the position of it. We can't tell the velocity yet. So that's what leads our engineer to do a little bit more study. So our engineer, unable to determine the velocity when it strikes the ground, decides I need to get more information. So he tries to mathematically model the instantaneous velocity of the object. So he does it again. He used one that has combined time photography to generate the following table. So instead of just being able to tell the total time it took to drop, he's able to tell the height at each different second. So if his camera measured at every tenth of a second, we see here, and he gets a height at every tenth of a second. And so the question is, how did he get the values over here in the third column? The answer to how did he get these values in the third column, without going back to our other sheet, is he basically just took those time intervals over. He took the average velocity since the last measurement. So before, we took it over the entire system. We took from time 0 to 0.6 and went from a height of 1.7658 down to 0. he's just using these much smaller increments. So for this height, he's going to take 1.71675, subtract 1.7658, and he's going to divide that by the change in time. So this was at time 0.1, this was at time 0, and so if I put those in my calculator, 1.1675, that's the number, minus 7.1658, I get negative 0.09, and divide that by, that's from 0.100 minus from time 0, I get negative 0.4095. To get to the second one, I would use the second set of data points. I would take the difference here, 1.5696 minus 1.71675, and again that's going from 0.2 to 0.1 from 0.1 seconds. So again, the same change in time on bottom, but when we calculate it out, we get a different average velocity. So we see the velocity, as we expected, is changing over time. Somewhere around the middle, it's somewhat close to what our middle point was, but not exactly. Somewhere around, we got that the average velocity is somewhere around 2.9, so that's somewhere near the middle of this, but it's not really consistent. So he does that. So he likes this idea so much that he has some idea what's going on now. So we could say that when it strikes the ground, it's getting closer to this negative 3.955. So this is similar to the velocity when it hits, but not quite close enough. So what does he do? Well, he got a better camera. I don't know where he's finding these faster cameras on the alien planet, but he gets one, and it takes pictures every 0.010 seconds, so 10 times as fast. So instead of every 10th of a second, now it's every 100th of a second. And we could generate this table again and we'd probably use Excel or something like that, put all those in there and do those calculations quickly, so I don't have to do it. Because now instead of 6 calculations that I've done here, I'm now doing 60 calculations. And also because I don't want to show all that, instead of writing out a giant table, he constructed a graph. So he built these 2 graphs. One of them had the height versus the time. So we see that graph looks something like that. And then the speed, or the velocity, well, he did speed. Remember, speed is just velocity without direction. So it's the absolute value of velocity. So the speed, turns out, made a nice linear graph. And so based on these 2 things, our alien engineer concluded a couple things. The velocity when it hit the ground is negative 5.84 meters per second. Okay? Which was, what we were getting closer to with our approximations to the nearest tenth. And if we had an even faster camera, we could do even better. If we were able to get down to the thousands of seconds, and we had 10 times as many measurements again, we could do any better. The other thing we noticed is that this looks like a straight line. We did this sort of thing back in the beginning of the semester, where we had velocity was a constant function of time. So that's nice. And it appears that this height function, if I get that back on the screen, is actually a quadratic function. It looks like one side of a parabola, or at least some downhill part of a parabola. So then he talks to a physics major and says, "Hey, I was taking all this data, and I found out, it looks like when I drop something that the height versus time goes as a parabola, and that the velocity of it looks like a linear function. And the physics major says, yeah, we did that a long time ago. Of course, that you can actually map that out using this equation that where y of t, or y of t is the height, is your initial height minus 4.905 times t squared. Well, how did he get that? Well, the physics major gets this because this has to do with acceleration due to gravity. Acceleration due to gravity is 9.81 meters per second squared. You take half of that, ends up being the coefficient there. So really what this looks like is y of t is y0, our initial height, or h0 as I called it previously, minus gravity over 2 times c, where this is acceleration due to gravity. So given those two things, then we want to try to figure out what is the velocity at a given time. So again, if we think about what's going on here, the way we were able to determine the average velocity at a given time, we went to that table, we picked a time, we got the height, y of t, for that time. And then we took the next part, which was that time plus whatever our step was, and we started out, we took, delta t equaled 0.1, so we only had a few points. Then we made it smaller and made delta t equals 0.01, and then we kept going. We could keep going and make that smaller and smaller. But whatever that delta t was, with the y value was just the new height was just y of whatever that new time was, t plus delta t. And so our velocity was the new height minus the old height over the new time minus the old time. If we simplify that a little bit, we get that it's y of t plus delta t minus y of t over delta t. Or the other way to say that is simply that we have delta y over delta t. So if we kept going on this forever, what would happen if delta t went to 10 to the minus 100? Or essentially what we're saying, so what if we made t almost 0, where we can barely see it? Well, that gets into the last concept that we talked about, which is the idea of a limit. So what is the limit as delta t goes to 0 of y of t plus delta t minus y of t over delta t? Well, we know we can't just plug in 0 because we get 0 in the denominator, and that falls apart. So what we actually get is that as this goes to 0, we have what we call a new function. So we know this is similar to delta y over delta t. As that goes to 0, we give that expression dy over dt as the change at an infinite time, and we call that the derivative. And we also sometimes notate that as with a prime mark there, y prime of t is another way we write the derivative. So this is the derivative of y with respect to t. So it turns out our instantaneous velocity which is the velocity at any given time, v of t, is this derivative. Because if we pick a small enough time to where there's no difference, we can't see the difference in time, then that velocity, that change in velocity we get there, is the derivative. So how do we use that? All right, so again, as I said, we explored this idea of the faster camera some more, and we broke it down into finding out we can get to the velocity is the derivative, something called the derivative of y with respect to t. And our physics friend told us that y of t equals 1.7658 minus 4.905 t squared. So we have this function. How do we get the derivative of it? Well, part E says we want to know that. So let's set that up. Part E says determine the velocity of an object when it strikes the ground. So what we know is that v of t is the derivative of t, and we know derivative of y with respect to t, and we know that y is this 1.7658 minus 0.4095 t squared. What we don't know is how we do any of that. And so when we don't know how to do something, what do? We start looking for help. And one of the things that we know for this class is we have those reference sheets we have that we gave you at the beginning of the semester that have lots of good formulas and stuff like that. So if we start looking through there, we quickly find one called the derivative. And so it talks about, yes, we've seen this before, that slope dy dt is the limit of delta y over delta t as t approaches 0, and how they come about that. It's also got some basic functions there at the bottom that we can use, and those will help us a lot. But really, if we flip it over, it's got a whole page of different differentiation rules, which means derivative rules. And really, these first 8 are really what are going to lead us, will solve most of the problems that we'll run into. We start getting into some trig functions, that sort of thing. There's stuff on down the page that will help a lot. But understanding these will solve a lot of our problems. So let's see how that might work. Okay, so here's the function that I'm trying to work with. I'm trying to find the derivative of this function. So one of the first rules that helps me out, if I see in here, is the law of subtraction. I have two terms being subtracted from each other. I see rule 4 tells me that the derivative of two things subtracted from each other is just the derivative of the two things individually subtracted from each other. So I can split them apart, which is very helpful. So let's do that. All right, so using that rule 4 for subtraction, I just split it into the two parts. I have those two things there. So that made things a little bit better. What else can I do? Well, let's look back at our sheet. Rule 1 tells me that the derivative of a constant equals 0. So let's use that. So if I put that into play, I use rule 1, which tells me that the derivative of a constant is just 0. So this first term is now 0. It goes away. Okay, so we solved that one. How else can I simplify this? Well, I've got a constant here times another function. Is there a rule that deals with that? Yeah, rule 2 says that I have a derivative of a constant times a function. It's the same as the constant times the derivative of that function. So I can just pull the constant out front. So let's see what that looks like. All right, so I use rule 2, and I simplified this down into pulling that constant out front. And now we just have a t squared term in the middle. So is there anything else that I can do to simplify this? I'll go back to my rule sheet. We use that. We don't have things added together. We're not doing products or chain rules. We're not using the power rule. The power rule is very helpful in solving polynomials. It tells us that if we have the variable raised to the n, then the derivative is that power, and we reduce the power by 1. So how does that work for our formula? So for hours, I'll keep my constant out front. I'm going to apply the power rule. So it says for the derivative of this, of t squared, I'm going to bring the 2 down front. I'm still going to have my variable, only now it's going to be to 1 less there. So I'm just going to have t to the first power. So I get that my derivative for the function is, by using one more step to simplify, equal negative 9.810 times t. That's my velocity at any given time. And if I remember back, the question I was trying to solve for part E was the velocity at 0.6000 seconds. It's just going to be what I get when I plug that value in there. Times 0.6000. So that value is negative 5.886. And the units of it, it's a velocity, so it's meters per second. And if we look and think back, when we looked at part B, and he was trying to figure out what the instantaneous velocity was, we got. So this is the answer to question B, which asks what is the instantaneous velocity, or what's the velocity when it strikes the ground? We noticed when we did things quicker, we got closer. We got negative 5.84. So using the camera that did hundredths of seconds, got pretty close when we compare that. But this is our actual answer to part B. That's how we can figure out what happens there. Part F, the student keeps going, says, well, if I took the derivative of the height and I got velocity, what happens if I take the derivative of velocity? Well, let's think about that a minute. So I want to know what is the derivative of the velocity. So my velocity function for this part is we just said it was negative 9.810 times t. We can apply some rules to that. We know that, again, we can pull out our constant. And then we know, well, two ways to look at it. One, you can see we have dt over dt. That's going to turn out to be 1. Or if we look at it from the larger perspective, that if we use our power rule, that this is going to be negative 9.810. Using the power rule says we would, since this is t to the first, have 1 times t to the 0. T to the 0 is 1. So that's just equal to negative 9.810. And what are the units on this? Well, this has units of meters per second, and we're taking respect to time. So it's actually going to have meters per second squared. And this should start looking like something familiar to you that we've used in previous homework assignments, which is that the derivative of a velocity with respect to time is equal to acceleration. Because again, if we think about it, it is the change in velocity over time. So how much is our velocity changing is acceleration, and specifically this one is g, which is acceleration due to gravity. Which is a constant we see many times. And so many times we will write this as a of t. So the key factors we learned here are that v of t is the derivative with respect to time of our position, and that acceleration is the derivative with respect to time of our velocity. And that's useful in many different applications, and we may have different functions that fit y. Sometimes y is a linear, sometimes it's quadratic, sometimes it will be a more complicated thing, but these principles will hold true. All right, so our friend, our alien engineer, has figured all this stuff out about acceleration and position and velocity, and says, okay, my physics buddy, what if I throw the object upward, releasing it at a height of 1.5 meters with an initial velocity of 4.50 meters per second? And the physics major says, well, then you'll just get this equation that says y of t is 1.5 plus 4.5 t minus 4.905, where y is the height in meters of the object's t seconds after it's released. All right. So then the engineer wants us to determine what's the velocity as a function of time after it's released, and what is the acceleration as a function of time when it's released from then. And so if we follow along with what the physics friend did, is he took our initial height, our initial velocity, and then we still use the acceleration due to gravity, half of that there, is how it adjusted our equation. And so what we want to determine in part G is velocity as a function of time. And we just said that that is the derivative of position, or as we'll start getting more used to writing these things, we'll just say that it's y prime of t. We talked about that being a short notation of that. Okay, so we're trying to find that, and that's our function, 1.500 plus 4.500 t minus 4.905 t squared. We learned from before that we can split things apart and do them. When we do addition and subtraction, we can do each part by itself. So rather than taking that as a separate step and splitting it out, we're going to get faster at these and just do each part and start to recognize these things. So we know that all this together, v of t, is going to equal, if I just take the derivative of each part, the derivative of a constant is 0. The derivative of a number of a constant times t to the first, well, t to the first, we know it's just going to go away and leave a 1 there. So I get 4.5 times a 1. And for this one, I get negative 4 I get my constant times the derivative of what's in there, which is 2t to the first. So I can simplify all of that. That goes away. This is just 4.5. This, 2 times that, is 9.810 t. So that's my velocity as a function of time. Using power rule and addition rule, if you need to check those things later. The addition rule is what tells me I can do each part one by one, and the power rule is what allows me to change the parts inside there. So I'm going to get that. And then what is the acceleration as a function of time? Well, acceleration as a function of time, we said, is the derivative of velocity. So if I take the derivative of this, I'm going to get 0. If I take the derivative of that, I just get a constant. Times 1. Again, eventually we'll get used to the habit of not even have to write that 1. We just know that if we have t to the first power, it's just whatever that constant is. So I get that the acceleration of t, acceleration as a function of time is just negative 9.810 is my value there. And we know that that's meters per second squared. Velocities will be measured in meters per second as we need those. So now at any time, we know the acceleration is the same, we can get the velocity, and we can figure out the height. Have all 3 functions there. Part H, find it on the page here, it says when does it reach its maximum height? So let's think about this and sketch it real quick. So we're throwing this ball up in the air. And it's going up, 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 and gravity's slowing it down. At some point, it reaches its maximum and starts coming back down until we hit the ground. And it wouldn't necessarily fall on the side, that's just me drawing poorly. So what's going on at the maximum height? Well, at the maximum height, gravity has slowed it down enough until it gets to 0, and then after that instance, the velocity goes negative. So at max height, v of t has to equal 0. Or the other way of saying that is that the change, that the derivative of our height with respect to time equals 0. So if we know that's the case, then we can just plug that in and figure it out. So we know that 0 is going to equal 4.500 minus 9.810 times t. We can move that to the other side and get that t is 4.500. It's going to be divided by 9.810. And if we want to punch that in, we get that that happens at 0.4587 seconds. And we went way out there in terms of significant figures because we seem to have devices that can measure at least to the nearest 100th second. So maybe we should round that to 0.49 seconds, 459 seconds. But yeah, we seem to be able to measure that accurately. So it reaches its maximum height at 4.59 seconds. The other thing he wants to know is what is the height of that second? At maximum. Well, to do that, all we have to do is that, so if we call this T max, Y max is just going to be Y of T max. So we can just take that value and plug it into our original equation. And this is where keeping the extra decimal points might actually help us. But it's just going to be 1.5 plus 4.5 times the 0.459 minus 0.4905 times 0.459 squared. So Y max is, so our maximum height is 2.53 meters. So with this tale of the alien engineer, we were able to determine a lot of key things. First, we learned about what a derivative was. Then we learned the relationship between position, velocity, and acceleration with respect to time. That, again, we have y of t. V of t is the derivative of y of t. And that a of t is the derivative of t. And it's actually what we call the second derivative of position. So meaning that we took a derivative twice to get to acceleration. And we learned the key concepts of using derivatives from the general formulas, which will really help us along the way.